Alright, hey everyone. Today was day 12 of Admin of Code, and today was about damaged and operational springs. And we have some information where the damaged ones and the operational ones are, and based on this information, I'm supposed to figure out how many possibilities there are to place the operational and all the damaged springs on a particular grid. So input will be lines, and in each line, the first part corresponds to the positions of the springs and whether they're operational or damaged. So each dot corresponds to an operational spring, and each number symbol corresponds to a damaged spring. And there's also these question marks where you don't know whether the springs at these positions are operational or damaged. But luckily, we got a second part of the input. So this list of numbers tells us that there is one damaged string followed by one or more operational springs. And then again, we have a damaged string followed by one or more operational strings. And finally, we have 3 damaged strings, and afterwards there can be some more operational springs. And then with this input for the first part, it determines where the damaged and where the operational springs have to be. So we have the first one and the third one would have to be damaged springs in order to get both these ones into the line. The second one has to be operational, and the last 3 we already know that they are damaged. For the second line, we have more options. So we have 4 options. So this particular position, we know that the spring at this position must be damaged to get our 3 damaged springs that we know there must be somewhere. And for these two and these two, we both have 2 choices. So either the first one could be damaged and the second one operational, or the other way around. The first one can be operational and the second one can be damaged. So that gives us 4 options in total. And for the whole puzzle, we just figure out for each line how many options are there to place the damaged springs, and then we sum this up for all the lines. Okay, so how do we do this in code? So first we use this state to represent the state of a spring. It can be either damaged, which would be a number symbol in the input. It can be operational, which would be the dot symbol in the input, or it can be unknown, which would be a question mark symbol in the input. And then for each line, we need to parse it. So for the first part, we just convert each character into a state and get a list of states this way. And for the second part, we just parse it into a list of integers that represent the counts. And then in order to solve the problems, we use a function that we will call iteratively. And this function gets us the number of solutions based on a particular list of states and a list of counts. So in order to do that, first we check if there is no counts left. So if all the counts were already placed before. So in this case, there are 2 possibilities. First, if any of the remaining states is damaged, then we know there's no possibility, so we return 0. The number of solutions will be 0. Otherwise, if all the remaining states are not damaged, then there is one possibility, so they're all operational, and this will be one possibility. Okay, otherwise, if there is at least 1 count left, what we do is we consider 2 possibilities. So first, the first position might be damaged, or the first position of the states might be operational. And for each of those possibilities, we count the number of solutions, then we add them up, and this will be our total solution. So for the first possibility, we want to consider the first position as if the first position is damaged. First, we want to figure out if that's actually possible. So in particular, if we can place the first count at index 0. So if this is the case, then we know that not just the first one position will be damaged, but also the second, third one, and so on. The number of them is given by this first count. And then after all the damaged ones, there must be 1 operational one. So this is the additional +1. And so the remaining states will start at first count +1. And then remaining counts will just be all the counts apart from the first one. And then based on these new states and new counts, we get the number of solutions, and that will be the first part of the number of solutions for our particular state and count. The second set of solutions will come from when the first position is operational. So first we need to check if the first state can be operational. So for this we need to have at least 1 state left. and the first state needs to be either operational or unknown. If this is the case, we can have the first state as operational. In this case, the remaining states will just be all the states apart from the first one, and then we count the solutions based on these new states, and we still have all the counts we had before, and we add that to the number solution. And then what we return is just the sum of those two values. That would be the number of solutions for a particular state and count. So we needed this can_place function above. So what does this do? So we can place a count at a particular index. To evaluate it, first we need to check if there's not enough states left. So if the index plus count is greater than the length of the states, it's not possible, so we return false. Then if any of the count states is actually operational, then we also return false. That does not allow us to add that many damaged states. And the final condition is that either there is no more states left afterwards. Also, if there are states left after the count, so this is this condition, and furthermore, like the next state is damaged, that is also illegal. So we know that the next state must be operational and not damaged. So we also return false. And that's the three possibilities how it can fail. Otherwise, we know we actually can place the count at the index. And yeah, that will allow us to solve the problem. So in order to solve it, we go for each line, parse the line, and then call this function, get a number of solutions, which will iteratively call itself again, but then eventually return the solution for the state and the count. And we add that to our global solution, and then the total solution would just be the sum of the solution for each line. All right. Of course, we should run our code on the test input. That looks good. So we also run it on the real input, and it also turns out it gives us the right solution. For part 2, it turns out the input is not supposed to be considered only once, but it actually is supposed to be repeated 5 times. So both the states and the counts are supposed to be repeated 5 times. And we could try to solve it with our original get number of solution function, but that does not run quick enough, so it's not efficient enough. So what we instead do is essentially have exactly the same function, but this time we cache it. So it turns out for the first part, we call this get number of solution function a lot of times with the same states and counts. So of course that's wasteful. We can just for a particular tuple of states and counts remember the result and not evaluate this get number of solution function again, but just look up the result in a dictionary. And this is exactly what this cache function does. So we need to make sure our inputs can be used as keys in the dictionary. So in this time we use tuples instead of lists, but that's the only change. The rest of the function stays exactly the same. And we use this decorator that caches the function in order to be more efficient in the evaluation. And then we can use this new cached function in order to solve the problem. So first we need to get our list of states. We told that we have the original states, then an unknown state, then again the originals, and so on. So we can construct the new states by repeating this states and followed by an unknown 4 times, and then added an additional 5th time. And the counts is just the original counts repeated 5 times. We convert both of them into tuples in order to evaluate them in this get numbers of solutions function that now is cached or is caching. And that evaluated for each line, and will give us the solution, so we just sum over all the lines. And we should also run this on the test input. That also looks good. So we also run it on the real input, and it also turns out it gives us the right solution. All right, that was it for day 12. See you around.